Thanks very much, Ruchi, and thanks very much to the organizer for having me. It's great to be here. And so the work I want to tell you about is joint work with Paul Wedrich, who is sitting on the first row, taking care of the video. And so it deals, it talks about, so I want to tell you about surface skein algebras that we've seen them in Tang's lectures, and talk a little about categorification results and a lot of perspectives and hopes for the upcoming year and probably the next one as well. So, okay, let's go with that. So the goal is to kind of explore categorification for the skein algebra of surfaces and try to get invariance out of that. So invariance. A little bit more precisely, the aspects that I care about are, first of all, define/study link homology for links in taken surfaces. And so the reason why I say define/study is because there already are existing constructions, in particular by Asaida, Chititsky, and Sikora. And so what I will be talking about today is a way to recover their construction, explain why it's the best thing to do and why it's a natural thing to do, and try to extend that a little. In particular, one thing that they don't see is a categorification of this stacking algebra product on the skein algebra of the surface. And the hope is that the point of view that we've adopted with Paul gives better tools to achieve that goal. But I announced a couple years ago that that will be done very soon, and I would definitely won't give you any answer in that direction, but hopefully within the next few years that will be done. Okay, so the two other things I want to emphasize are a little bit more exploratory. First one is, well, if we build all of these tools, they should be put to use in some way. So I want to use these categorification tools to do something, and especially to prove things. And so what I will be talking about. Oh, should I get plugged in? Should I just, put it in my pocket? All right. So I want to use these categorification tools that we're trying to build to do actual things and say things about the original objects, which is often something there's a way we try to sell categorification. And in particular, I want to try to prove things about positivity. So I will mainly give you positivity conjectures and maybe give some idea as to why we believe that what we have is are good tools. And the last thing is that we want to go to three manifolds, and this is completely exploratory. So let me maybe start with the last point so that we we can go to more precise things later. So somehow the motivating question is let's take M, a closed compact three-manifold. And the question is, how can one extend the Jones polynomial for links in, say, R3 to some meaningful invariant of M? So there are basically two known ways to do that. And the first one is say, well, M can always be presented as surgery of S3 along some link L, which means that for all M there exists a link such that if you take S3 minus, you remove some tubular neighborhood of the link, and then, so here is at something like D2 cross S1. The boundary of that is S1 cross S1. And you can glue along this an S1 cross D2, and you get a different three-manifold. And so the theorem of Wallace and Licorice is that any three-manifold can be achieved in this way. And so that gives a way to have a link appear in the picture from three-manifolds. Then we have the Jones polynomial that compute invariance of links. And so maybe there's a good way to extend the Jones polynomial to an invariant of the underlying three-manifolds. And so the trouble when trying to do that is that, and this is the theorem of Kirby, L and L prime, the surgery of S3 along L will give the same three-manifold as the surgery of S3 along L prime, if and only if L and L prime are related through Reidemeister moves, so that's fine. But also two extra moves, which are basically that if you perform surgery along this link, that's the same as doing nothing. And the second one is that whenever you have something that looks like that, so you have two strands that go close to each other, you can slide one strand around the other one, so follow it parallel, and the result will again be unchanged. So these are K1 and K2. Okay, so what Witten, Reshtikin, and Turayev did well, the first remark is that the Jones polynomial is indeed invariant in the Reidemeister move, so that's fine, but it's not, if you do computation, you will quickly realize that it's not invariant under these two moves. Yeah?
In the K2 move, you have like the things outside of the small ball that are different, so I don't quite see both words.
So you take some small ball where you see two strands, yeah. And then, so if I'm not wrong, the trick is that okay, so yeah, let me do an example. So very easy one is you have, okay, a slightly more difficult one. I'm not sure I'm able to draw a trefoil. Right, and I'll take two colors. So if you are in, say, this situation, then you can replace by same trefoil here. and you have something that follows the curve, comes back around here, and then you go back to that strand. And so the claim is that both. I think I got the framings right, but so the main idea is something around these lines. So the point is that that's a not really local move, so it can be terrible to prove. Okay, and so the idea of Witten, Reshetikhin, and Turayev was that if you take Q to be a root of unity, and then you define the sum, well, some coefficient times the sum of the dimension of Vi times the Jones polynomial of L taken with color Vi, where Vi is sim I of C2, C2Q, or C2, then this is invariant. Okay, so for categorification purposes, there are lots of difficulties in categorifying this kind of expression and so on. But probably the first big difficulty is that we're working at Q to the R equals 1, and categorification at roots of unity, at least to me, it's some PDG nightmare. So if you want to know more about this definition, ask Josh and Chiyu and Kovanov and Ben Elias. But this is all a somewhat difficult machinery. So the kind of original hope that we had with Paul was that maybe there could be some alternate way to extend the Jones polynomial to three-manifold that's more accessible from categorification perspective. And so somehow the other reasonable way to extend the Jones polynomial to three-manifold is to go through skein modules, as Tang told us. And so the skein of M is the, so I'll take, say, Z of A plus minus 1 span of links in M, modular relations, which are a crossing equals A times one smoothing plus A inverse times the other one, and a trivial link goes to minus A to minus A minus 2. So for a general three-manifold, there is no such thing as a diagram of a link because we have no preferred direction of projection, no preferred surface where to project. But the same relation can be understood as if you find a three-ball in the three-manifold that has that has the direction of projection in which you can find such a diagram, then you can do all of that. And so this was introduced by Pshititsky and Turayev. Okay. So the original hope was that this construction holds, so A and Q are, I think A is the square root of Q, so A and Q are basically the same thing. So the nice thing about this construction is that it doesn't require to take Q equals, Q to be a root of unity, so that should relieve a lot of the categorification issues that we have in the first, following the first program. It's actually not so true because the trouble with skein of M is that it has torsion. That's associated to finding some essential non-separating, I think, or separating tori and spheres. So in a lot of situations, you will have torsion in that, and I'm not quite sure what that will mean for in the categorified setting. So so that was just to say that it won't be a peaceful road either. Okay, but still, it's still an interesting question, and somehow I think a nice way to attack it is to present M, instead of looking at M as realized by surgery on the link, you can take a Higard splitting for it. So any three-manifold can be realized as the gluing of two handle bodies of the same genus along their common boundary. And that gives rise to an isomorphism, skein of M, isomorphic to skein of AG, tensor skein of AG, and the tensor products taken over the skein, skein of the middle surface. So what we're saying is that if you find a way to understand, categorification of the two handle bodies, this is not too hard. There are existing constructions. At least it seems like something reachable. And the first thing to study, basically what I'm saying, if you want to take a tensor product of two modules over an algebra and you want to categorize that, you better start categorizing the algebra and then you see what happens with the next steps. So step one is let's try to categorify this one. So that's what I want to talk about. And so the important piece that we want to understand in that is not only a categorification as a module, but most importantly, categorification as an algebra. And this is really what we want to lift. Okay. And I should give the references for that. So what do we know about such categorification so far? That's been categorized by Kovanov and say Barnatan for the version we care about, for when S is R2. It's been categorized by Roberts, Asaida, Pshititsky, Sikora, and further studied by Grigsby, Licata, Verli, in the case of the annulus. And I really have no space anymore. And so Asaida, Pshititsky, Sikora did the case of any surface, but without the product. And so on the other side, just for comparison, in that case, on the Brzezinski side, there aren't many known categorifications. There's something in S2 times S1 due to Lev Rozonsky, and it's been recently extended to a slightly more general setting. So far we really have very, very little on that side.
Is this formally true that skein of M is the tensor product?
I think so. So basically, if you take a link in, so you take a link in there, you can, and you choose a skeleton for both handle bodies, then you can have your link avoid the skeletons, and you push it on the middle surface.
Yes, but maybe you have a deformation of it, which somehow happens outside.
But so.
It's not obvious if it's true.
So there clearly is a map going that way, if what I said is true. I thought it was an ISO, but I might be wrong there. Is this true? But isn't it an ISO?
And is there more relations? That's what I'm saying. There is a method.
I think there is a map.
Okay. No, the ISO isn't so clear, but okay, so maybe question mark.
Because you can have leads crossing.
Yeah, you might need to combine relations on both sides, but I thought that taking the tensor product over the middle algebra will take care of that.
Is it subjective if you have, say, something that runs over the one handles in one handle body and then also in the other handle body?
Yeah. So basically, you can always avoid. So choosing like a skeleton graph for both handle bodies, you can always avoid these graphs, and then you have a preferred direction of projection. So I think that part is solid. The other direction is maybe a little weaker. Okay. So it won't endanger any of what follows because we're so far away from categorifying it all that. Okay, so let me step back and write just a few reminders on skein modules so that we just on the same page. So, so the skein module of S was defined as Z A plus or minus 1 spanned by links in S cross 0, 1, or equivalently in that case, diagrams on S, mod red minus move. Modulo two relations, which are that one can smooth crossing and one can get rid of trivial components. And Teng gave us already a basis for this module, which is given by multi-curves. Meaning, so we always have the empty curve together with disjoint union of simple closed curves. So in the case where S is, say, R2, then we've seen that the skein module is just isomorphing to the base ring, and this recovers the Jones polynomial. An interesting example that already has some of the difficult features, but is still very manageable, is the case of the torus. And the nice thing in that case is that the multi-curve basis is very easy to understand, mostly because once you've chosen a base curve, a first curve, if you want to put more curves that do not intersect the first one, the only choice is to have parallels of this given curve. So that wouldn't be true for a more general surface. But here, all I can do is take more copies of the same curve. Okay, so that's pretty cool because simple closed curves on the torus are easy to understand, easy to index. And so all that can all be indexed by choosing a particular slope for the base curve, so a pair of coprime integers. And then you just take parallel copies of that, and that all gives a basis for the skein module of the secant torus. And for higher genius, then it can get quite wide. And so all of this has an algebra structure by stacking. And let me just write a very quick example. So if I want to multiply this curve by this curve.
So what is the answer for those?
For what?
What is skein algebra in case of torus?
So, so as a module, it's a direct sum of one copy of n plus for each pair of coprime integers plus the empty curve. So my point is that as a vector space, this choice of you have as many generators as parallel copies of coprime integers.
But you have to identify n and minus n.
Yeah, so that should be the basis is indexed by, so you have the empty one together with m n k with m greater or equal than 0 and n in Z unless m is 0, in which case I want n to be strictly greater than 0. And k lives in n plus. So I think this gives a basis for the module. Okay, so multiplication goes by stacking. And then resolving. So that's A times this one plus A inverse times this one. So this very easy example actually already kind of shows the basic thing I want to state next, is that if I take two elements in my basis, I multiply them together, and then I expand in terms of the basis elements, the result is a linear combination with polynomial coefficients, the coefficients of which are all positive. So it's very easy. We have two monomials with coefficient 1 in both cases. So this shows a positivity phenomenon that we want to try to understand better. So what do we mean about positivity? So a basis C is positive if for all x prime in C, one can expand the product of x prime in terms of a sum for y in C of py y. So far I'm just saying that C is a basis, so the product of x with x prime, that's an element of the skein module, and I can look at its coordinates in the given basis. And so it's positive if all my py's belong to n of a plus or minus 1. So the important part is here. Okay, so it appears that it's quite easy to see that the basis B, that we chose, that we chose here. Let me call that B. So this one is not positive. I think that one can fairly easily see that by computing something like that. So two parallel copies that way, two parallel copies that way, that will definitely fail. But it turns out that there is another basis that's positive. So if one considers, so let me define Chebyshev polynomials. So T0 equals 2, T1 equals x, and Tn equals x, Tn minus 1 minus Tn minus 2. So these are called Chebyshev polynomials of the first kind. And just for the sake of completeness, if we had done a slight change, so if we start with 1 instead of 2, and same afterwards, then that's called Chebyshev polynomial of the second kind, which is easy to remember because you just swap the first value and that gives you the kind. Okay, so the conjecture of Fogg and Goncharov that's been explained in that setting by Thurston, Dylan, is that if you take TB, which is the same as B, but instead of taking all multicurves, you take this joint union of T of gamma, Tn gamma, for gamma of say homeoclasses. So my point is I don't want to take parallel copies. If I have parallel copies, I want to take a Chebyshev polynomial of the base curve. Then this basis is positive in skein S. So if S is S1 cross S1, then this was already known, and it follows from a theorem of Froman and Jelka from 2000. And what they did is they actually computed explicitly what the multiplication rule is in that new basis. So they give us the expansion formula here. They show that it's actually a very simple one. And that automatically shows that, that from there you can very easily read that the basis is positive. The other case where it's known is that if you take A equals 1, then that's a result of Thurston in the same paper. And that holds for any surface. And what Tang tells us is that if you find a positive basis and you consider Chebyshev polynomials in that basis, then that's even more positive, if I got the result correctly. So somehow that considering Chebyshev polynomials of whatever basis you care about is a good idea. Okay. So what's the goal for the next 20 minutes? We'll try to, so I'll tell you some construction of a categorified version of the skein module. So what we'll try to do is understand that better. First, get invariants for links out of that, and then see what we can say about positivity conjectures. So the good news here is that this was basically done from the very beginning of Kovanov homology. So Barnatan version of Kovanov homology is based on a a category of cobordisms that extends at absolutely zero cost to the case of surfaces. So let me call cob S the category of cobordism over S with objects multi-curves on S together with a notion of direct sum. And morphisms will be cobordisms inside S cross interval. And so we take matrices of such because we want it to be compatible with the additive structure.
So what is the direct sum? Is formal direct sum?
Yeah, exactly. And furthermore, I want to make it graded, so there will be a grading shift. And so this category is graded, and the notion of degree here is minus the Euler characteristic. So right. So the claim, which is a little informal here, and I think it's way easier to make it formal at the very end of my talk, but it's not, well, yeah. What I want to make is that the Grothendieck group of this category is the skein module of S, which is basically just extending. So if S was R2, this is compatible with the fact that covariant of homology categorifies the Kaufman bracket, so the Jones polynomial of the link. And so the other nice property of this construction is that the original definition of the not invariant, so meaning of covariant of homology, extends as well at strictly no cost, because you just say that. So my point is that all of the definitions that arise in this Barnard version of covariant of homology are local and take place in a small three ball. So we just send three balls into the thickened surface, and it all goes exactly unchanged. So just as before, crossings get sent to some small two-step complexes, where the differential is given by an elementary saddle cobordism. Same for the other crossing. And that all goes through, and you get an invariant out of that. Which is, so what you get is some kind of, so something associated to a link diagram or not diagram that lives in the category of complexes up to homotopy over the category of cobordism over S. So the good news is that this is super easy. All right, so Right, the good news is, well, this is super easy to define, but the bad news is that you get something that lives in the category of complexes over the category of cobordism over your surface, and you basically cannot do anything out of that because that's not very handy. So the solution to this issue that was developed by Asaeda, Pshizitsky, and Sikora consisted in saying that it will be way easier to have an actual complex in a category of vector spaces associated to a link diagram instead of some formal complex in some homotopy category over a complicated category. So to do that, Asaeda, Pshizitsky, and Sikora actually wrote down a TQFT functor going from cob S to some category of vector spaces. And so I won't give the precise definition because the point I want to make is that the functors I gave explicitly by looking at generators and checking relation and so on is actually entirely natural from the point of view that we've adopted with Paul. But let me briefly outline the general idea is that they started listing all generating morphisms in the category. And wrote down what the image should be. And so far it looks like just usual. You just list generators of the cobordism category. But then at some point you realize that if you live over a surface, it's slightly more complicated, and there is a new cobordism that appears, and that you cannot avoid. And to see that, right, let's reconsider the image that's just at the top of this board. If you want to lift this up to the categorical level, then you will need to relate the two different resolutions of my link diagram by a saddle cobordism. So this will be something mapping from here to there. That's a saddle cobordism over this small region, and an identity cobordism everywhere else. So I won't attempt to draw it because I think that when I draw it, it doesn't make it any clearer. But you can try to picture that in your head. So the point is that this new cobordism is not generated by a composition of those. And one way to see that is that basically we're trying to do a pair of pants, but with only one leg, because I only have one connected component of both sides. Yeah? Yeah, exactly. So I will draw it. So the first thing is, if I just draw what's happening in this small region, what we have at the top is something like that, and at the bottom, something like that. And so in between, we just put the saddle cobordism. So that's right, and so in between something like that. And then everything else is glued with, I put an identity cobordism everywhere else, and I just glue along the common boundary. You can try to draw that on the torus, but it's usually not very enlightening. So I want to do something like where I put a saddle cobordism over here, reach something that's here, and then I put an identity cobordism everywhere else. So yeah. Well, maybe an interesting point to note here is that this cobordism is actually unorientable. So what happened is that in the cube of resolution associated to the link diagram, one naturally sees an unorientable cobordism show up that never showed up in covariant homology over the disk. So what Asaeda, Apsicity, and Sikora say is, okay, we don't know that cobordism, so let's just send that to 0. And it's been further studied by Turayev and Turner. And basically, I think I can sum up the conclusion by saying you have no choice. This is the only thing to do. Okay. Maybe a side remark about that is that if you do, so I don't know, go to the next board. So I have 10 more minutes. Or? About that? 13? Oh, thanks. Well, I should have erased better in that case. Right, so a side remark is that if you look at this cobordism, oh, sorry, I realized I completely forgot to give you the relation for the Barnard category. I should have done that. So these cobordisms are considered up to some relations that has the fact that a sphere is 0 and a torus equals 2, and any cylinder can be cut as follows. Well, let me put a 2 here. Right, so it's a quotient of the cobordism category. And again, these relations are just directly imported from covariant homology over the disk. So if you start from here, you perform the cobordism that we said that goes to here. And then if you decide to come back here, the cobordism you get that way is an endomorphism of that curve. And it's maybe a very easy exercise to check that it equals to an identity with, so it's just this. So what we're saying is that if the TQFT functor kills this cobordism because it's unorientable, then the image of that should as well be 0. So it's maybe not such a big deal, but what it's saying is that all of the higher degree part of the endomorphism space of this curve will be killed by the TQFT functor. So that's, that's a restriction to consider. And so the way that Asaeda, Apsicity, and Sikora prove that what they had written indeed gives a knot invariant, just that they looked at each of the Rademacher moves and explicitly prove that if you apply the TQFT functor for all closures of the two versions, then you do get the same thing. So it's a very hands-on computation. So the first result we obtained with Paul is that this category cob S can be endowed with a non-negative grading and well, let's say that first statement. And once you've done that, the APS TQFT is more or less the restriction of Kovanov's TQFT to the degree 0 part of the category. So what am I saying here? Well, the first thing is a very general statement, is that if C is a category that's non-negatively graded, then you can write C equals C0, and it gets in direct sum with the strictly positive part. And if you have a complex in some category of cobordism of complexes over C, then because of the non-negative grading, you know that D splits into D0 plus a strictly positive part. And then you have that K D0 is a complex well-defined up to homotopy in the category of complexes over the degree 0 part of the category. So which I'm saying is that if you just have a graded category, you cannot decide suddenly that you want to restrict to the degree 0 part, because there is no reason why a complex, so the degree 0 part of a complex has no reason to be a complex. But if the category is non-negatively graded, then that becomes true. So, so that's why we cared about non-negative grading. So I'll more or less keep the proof, but I can give you an idea for it. And the base idea is that, well, I can at least tell you how we endow these categories of non-negative grading. And the idea is that you start from the cobordism category, and you find a full subcategory where you have less objects, and you just model it on what happens in the skein, at the skein level. So you go to the subcategory which only contains, so the sub, well, let's call it B cobers, which is the one where I only want objects to be those that appear in the basis B. So what we're doing, we just throw away all of the trivial components, and that's all. And so once you've done that, this category is graded just because it's a full subcategory of a graded category, and this is the one that's non-negatively graded. So the original grading on this category induces a grading on the subcategory, and then because this is an equivalence of categories, you can induce back a grading on the first category. So basically by throwing away all the part of the grading that was affecting only cobordism that do not play with the topology of the surface. Right. So the next remark I can maybe just say is that the reason I wrote more or less here is that the original Kovanov's TQFT, the original Kovanov construction, is actually not really functorial. It's functorial up to sign. And so there is some sign issue in all of this story. And to make it all more precise, one should go to one of the functional construction. And if you do so, so for example, if you use Christian Blanchet's foam construction for it, then you have something fully functorial. And the magical situation here is that if you redo the computation over here in this new functorial situation, then you don't get that, you just get 0 for some orientation reason. And so what I'm saying is that you can very safely kill all of the non-orientable part of your enhanced cobordism category while not killing the higher degree part. And so that's great news because from there you have, well, you keep a category that's way more manageable because you've thrown away all of the unorientable part, but you still have higher degrees that allows you to start building spectral sequences and all of that. So there is a lot of homological algebra that's allowed in this slightly different setting that wasn't apparent in the original APS construction. For the last two or three minutes, I'll maybe just jump right away to positivity questions, because yeah. So the first remark is all what we've done with restricting this category and so on, it hasn't affected at all the skein module. So that's great news because we can go to way simpler categories and we'll still have a categorification of the skein module. So what I'm saying is that if you take the K0 and furthermore you can throw in idempotence of the degree 0 part of the cobordism category, that's still isomorphic to the skein module. Okay, so we can play with this category and claim that we're working in a categorified skein module. And so then we have a classification theorem that tells you that if the base surface is S1 cross S1, then the simples in this category are in one-to-one correspondence with TB. So the base is made of Chebyshev polynomials of the first kind applying to multiplets. But which is fun is that if S is anything else, then the simples are in one-to-one correspondence with SB, the same basis, but when you use the other kind of Chebyshev polynomial. So, in a way, in this positivity conjecture, if you want to extend the result of positivity in the torus, you would hope that the simple in your category, which should correspond to basis element in the skein algebra, well, should extend from the torus case as well into something indexed by Chebyshev polynomials of the same kind. So this happens to not be the case. And so this motivated this slightly different formulation for the conjecture. Which is that if S is not S1 cross S1, then SB is positive in skein S. And just to give you the 30 seconds ID of this construction, the reason why this changes is that if you choose k copies of a simple curve and you restrict to the degree 0 category, in general, the endomorphism algebra of this thing, it will just be spanned by some I don't know, some tangle diagram or some temporal ellipse diagram, even better here, times S1. So which I'm saying is that this is the same as just dots cross S1. And one can show that if you put a temporal ellipse diagram between dots and you cross that with S1, in general, you span the cobordism category in degree 0. So here, these Chebyshev polynomials, they correspond to putting a Jones-Wenzel projector and hitting that with S1. What happens here is that you can still do the same, but over the torus, there is something special, which is that when you're looking at the endomorphism algebra of a curve, from what I said, here you should only see TL1, which is just the identity. And that fails for the torus because you can take your curve and have it go around and back, hit that with a S1. And so that's still degree 0. So for the torus, we have an extra endomorphism, and looking at, well, that causes this object to break again in the Karoubi envelope. And so what we're doing in this setting is further breaking this object here, so the symmetric representation of, symmetric power of the vector representation of SL2 into weight spaces. And this is why we see the special elements appearing. Okay, I had written my good resolution list for 2019, and I thought that having it recorded would force me to do them, but for time reason, I can't. So thanks very much.